Welcome to the deep dive. Ready to go on a journey with me today?
Always.
Awesome. Well, today we're diving into the world of light.
Ooh, fascinating.
I know, right? We're going to be using excerpts from an article called The Modern Understanding of Light.
Sounds promising.
It is. But don't worry, this isn't going to be some dry, boring lecture. We're going way beyond just like the textbook stuff.
Awesome. I'm in.
Okay, so this article starts off with a real head scratcher.
Okay. What's it?
It says light acts as both a wave and a particle.
Whoa. How is that even possible?
Right, that's what I thought.
Well, it is. It's actually one of the most mind-boggling concepts in all of physics, but honestly, it's been proven over and over again through tons of experiments. So imagine like a beam of light. Picture it traveling in waves.
Like ripples on a pond.
Exactly, like ripples on a pond. But here's the thing. It's also made up of these teeny tiny packets of energy.
What are those called?
They're called photons, and they act like individual particles. So it's both a wave and a particle.
I'm trying to wrap my head around that. So is this where all the quantum mechanics stuff comes in?
Exactly. You got it. Quantum mechanics is the study of how things work at like the atomic level, even smaller, the subatomic level. And this wave-particle duality, it's really front and center there. It's like a whole new way of looking at, well, everything, the whole universe.
Whoa, okay. I'm definitely intrigued. But before we get too deep into quantum mechanics, let's back up a bit. This article mentions some like ancient thinkers, way back in the day who were already fascinated by light. Like think Pythagoras.
Oh, yeah, Pythagoras. I mean, those guys were asking some pretty big fundamental questions. I mean, questions that we still grapple with today, to be honest.
Yeah, what were they trying to figure out?
Well, think about it. What is light even made of? How does it travel? How do we even see it? I mean, obviously, they didn't have the tools, they didn't have like the scientific methods that we have today to
Yeah.
actually answer these questions definitively. But their questions, their inquiries, those were so important. They laid the groundwork for centuries of, well, scientific exploration. So we owe them a lot.
Yeah, we do. And then, we fast forward a bunch of centuries to like the Renaissance. You got all these brilliant minds like Galileo, Kepler. But honestly, I think the real rock star here is Isaac Newton, right?
Totally. I mean, Newton's contributions to the field of optics,
Yeah.
groundbreaking, totally groundbreaking. He developed this thing called the particle theory of light. It actually explained a lot of light's observable properties at the time.
Okay, so help me understand, what does that mean?
Okay, so basically, imagine light as like this stream of tiny, tiny particles. They're bouncing off objects, right? That's how he explained reflection, for example.
Okay, I think I'm following you. But hold on a second. Didn't you just say that light is also a wave?
Oh, yeah, I did. And, well, that's where the story takes another turn. It gets even more interesting. See, Newton's theory, it worked well for a while, but there was some phenomena that it just couldn't quite explain.
Okay, like what? What couldn't it explain?
Well, think about what happens when you drop, like, two pebbles into a pond.
Right.
You get those ripples, and they, like, interfere with each other, right?
Yeah.
They create a pattern of peaks and troughs. Light does the same thing. But if light was just particles, only particles, how could it do that? How could it create these interference patterns?
So someone had to like come along and challenge Newton's theory. I mean, was he just wrong?
Well, not entirely. He was describing one side of it, one aspect of light's behavior. Remember, it's got that dual nature. But someone did need to come along and, well, sort of fill in the gaps, I guess. And in the 19th century, that's exactly what happened. Scientists like Thomas Young and Augustin Jean Fresnel, they conducted all these experiments with diffraction and interference.
And what did they find?
Well, they proved conclusively that light behaves like a wave. And this led to something called the wave theory of light. And guess what? The wave theory explained those phenomena beautifully. So well, in fact, that it kind of took over for a while.
So just to recap a bit here, we've got ancient philosophers, right? They're just like thinking about light, pondering it. Then we've got Newton's particle theory. And then the wave theory takes over in the 19th century.
Yep, you got it.
So where do we go from here? What happens next?
Oh, this is where things get really, really exciting. Just as scientists thought, okay, we have light figured out, along comes this guy named James Clerk Maxwell. And, well, let's just say he changed everything.
Let me stop right there. You're going to have to tell me all about Maxwell and his impact on our understanding of light, but that's going to have to wait until part 2 of this deep dive.
Stay tuned. It's going to be a wild ride.
All right, so where were we?
Well, you were about to tell me how James Clerk Maxwell, like, totally blew everyone's minds when he came onto the scene. Oh, right. Yeah, Maxwell. Okay, so picture the scene, right? It's the late 19th century. Scientists are feeling pretty good about themselves. They've got this like wave theory of light. It explains all these phenomena. They think they've got light all figured out. And then, boom, Maxwell comes along and drops this bomb.
A bomb, huh? Okay, I'm all ears. Tell him what Maxwell did that was so, like, earth-shattering.
He basically, well, he unified everything. He took electricity, magnetism, and optics, and he like brought them all together into this single, really elegant theory. He was amazing.
Whoa, hold on. So he's saying that electricity and magnetism and laity, they're all connected.
Exactly. And you know what? It turns out that light, it's not just any wave, it's an electromagnetic wave.
An electromagnetic wave? Okay, I'm trying to follow you here. Can you break that down for me a bit? Like, what does that even mean?
Well, it means that light is like fundamentally connected to these forces of nature.
Right.
Electricity, magnetism, they're not separate things, they're intertwined. Think about it this way. You've got radio waves, right? You've got microwaves, X-rays. They're all part of the same spectrum, the electromagnetic spectrum. And the only thing that's different between them, their wavelengths and their frequencies. That's it.
Wow. Okay, I'm officially mind blown. So by the end of the 19th century, we've got Maxwell's equations, we've got this understanding that light is an electromagnetic wave. Case closed, right? Everyone can pack up and go home. We've solved the mysteries of light.
Oh, I wish. Science is never that simple.
Yeah.
It never really stands still. There's always more to learn. And just when physicists thought they had it all figured out, along comes the 20th century and bam, another revolution. The quantum revolution.
Oh boy. I have a feeling things are about to get really, really weird, aren't they?
Yeah, you're definitely right about that. It all started with this thing called black body radiation. Ever heard of it?
Black body radiation. That sounds kind of spooky, actually. Like, what is that?
Okay, so imagine you've got this object. It absorbs like every single bit of radiation that hits it.
Right.
It's like the ultimate absorber of light. Now, you heat this object up, what happens?
I don't know. It gets hot.
Yeah, but it also starts to emit radiation.
Right.
And the weird thing was, the spectrum of this radiation, the colors of light, basically, it didn't match up with what classical physics was predicting at all.
So the experiments weren't matching the theory? That usually means somebody's about to come along and shake things up, right?
Right. And, well, that somebody was Max Planck.
Max Planck. Okay, tell me about him.
So it's 1900. Planck comes along and says, hey, I've got this, like, radical idea. He suggests that energy, it's not continuous. Like, it doesn't just flow smoothly. It comes in these, like, little discrete packets. And he calls these packets quanta.
Quanta. So instead of energy like flowing like water, it's more like, well, what? Little bundles of energy, like Lego blocks or something.
Yeah, exactly. It's like you can only buy water in 1 liter bottles.
Right.
So you can have 1 liter, 2 liters, 3 liters, but you can't have like 1.5 liters because you can't just, split a bottle in half.
Oh, okay. I'm kind of getting that. So energy comes in these like set amounts, these quanta, but I still don't get how this relates back to light. You know what I mean?
Well, a few years later, this guy named Einstein, I'm sure you've heard of him, comes along and he's like, hey, Planck's idea about quanta? Yeah. That applies to light too. Light comes in quanta. And he used this idea, this concept, to explain this thing called the photoelectric effect.
The photoelectric effect. Okay, help me remember. What's that again?
Okay, so imagine you're shining light on like a metal surface, right? And sometimes when you do this, it causes electrons to like fly off the metal. They get ejected. But here's the thing that's super weird. The energy of these electrons, it doesn't depend on how intense the light is. It depends on the frequency of the light.
That is weird. So like brighter light doesn't mean more energetic electrons. That doesn't make sense.
Exactly. That's why classical physics couldn't explain it. But Einstein, he can explain it, using this quanta idea.
Okay, how? How did he explain it?
He said that light is made up of these like tiny little packets of energy, these photons. And each photon, it carries a specific amount of energy, and the amount is determined by its frequency. So it's not the total amount of light that matters, it's the energy of each individual photon. Makes sense, right?
So are we like back to the particle theory of light then?
In a way, yeah. Kind of. But it's still not that simple. Remember, it's both. Light is both a wave and a particle. It's both things at the same time. That's what makes this wave-particle duality so mind-blowing.
Okay, so I'm trying to keep up here. We've got Planck saying that energy is quantized.
Right.
And then Einstein comes along and says, hey, guess what? Light is made up of photons. So where do we go from here? What happens next in this crazy story of light?
Well, all of these ideas, all these new concepts, they led to, you guessed it, a complete revolution in the world of physics. A whole new field, actually. Quantum mechanics. You probably heard of it.
Oh,
right?
yeah. I mean, it's kind of a big deal, right?
It is. And scientists like Niels Bohr, Lou Broglie, Werner Heisenberg, these guys, they took this theory and they like ran with it. They developed it even further. And you know what they found out?
What? Tell me.
This wave particle duality, it's not just for light. It applies to all matter,
Right
everything.
on.
It's like this fundamental principle of how the universe works. Isn't that amazing?
It's mind-blowing for sure. But I've got to ask, and I think I'm speaking for some of our listeners here too, like, why should anyone care about this quantum stuff? It seems so abstract, so theoretical. Like, how does this affect my everyday life?
Oh, I get that. It might seem that way, but honestly, it's the foundation for so many of the technologies we use every single day. Lasers, LEDs,
Yeah.
transistors, solar panels, all of these rely on our understanding of quantum mechanics and of light, of course.
Wow. I never really thought about it that way. Okay, so we've gone down this like deep, deep rabbit hole of wave particle duality. My brain is definitely feeling a little full right now, but I want to like come up for air a bit and get back to like some of the more, well, I guess you could say straightforward properties of light. So, what else does this article tell us?
Well, let's start with something pretty basic, speed.
The speed. Yeah, everyone knows light travels fast.
It does. It travels at like 299,792,458 meters per second in a vacuum.
Whoa, okay. You lost me with all those numbers. That's like
Mm.
ridiculously fast. It's hard to even imagine how fast that is. But here's a question. Does light always travel at that speed?
Well, that's the speed limit. But when light travels through different media, like air or water, it actually slows down.
Mm.
And this is why we get things like refraction, where light bends when it, passes from one medium to another.
Ah, okay. Like
What?
that whole thing where a straw looks broken in a glass of water.
Exactly. That's because the light speed is changing as it passes from the air into the water.
Cool. So we've got speed. What else? What are some other properties of light we should know about?
Well, the article also talks about wavelength and frequency.
Oh, yeah. Wavelength and frequency. Okay. Those seem important. Can you break those down for us?
Okay, sure. So imagine a wave,
Right.
any wave, like a water wave or, well, a light wave. The wavelength is basically the distance between two crests of the wave. You with me so far?
Yeah, I'm picturing it.
Okay, good. And the frequency. That's how many waves pass a given point per second. You got that?
Yeah, I think so.
Yeah.
So, like, if I'm thinking about a light wave, like, I don't know, a wave in the ocean, if it's a long, lazy wave, that would have a long wavelength and a low frequency, right? But if it's all choppy and the waves are coming in super fast, that's a short wavelength and a high frequency.
That's a great analogy. You got it.
Yeah.
And guess what? The same thing applies to light. Different colors of light actually have different wavelengths and frequencies.
Oh, okay. So, like, red light has a different wavelength than blue light.
Exactly. Red light has the longest wavelength and the lowest frequency in the visible spectrum, while violet light, that's got the shortest wavelength and the highest frequency. It's pretty cool, right?
Yeah, that makes sense. So, that's why we see a rainbow when white light passes through a prism, right?
Bingo. The prism is separating all the different wavelengths, so each color in the rainbow, it corresponds to a specific wavelength and frequency. It's like its own unique fingerprint.
Okay, awesome. So we've covered speed, wavelength, and frequency. What other cool properties of light do we need to know about?
Well, there's polarization. This one can be a little tricky to wrap your head around. But basically, imagine a light wave oscillating, you know, like vibrating in a specific direction. Polarization describes like the orientation of those oscillations. So unpolarized light, like sunlight, has waves vibrating in all these random directions. But polarized light, like the light that passes through some sunglasses, has waves that are vibrating in just one direction.
Oh, okay. So, like, polarized sunglasses, they filter out all the light that's vibrating the wrong way, and that's how they reduce glare.
You got it. Exactly how it works. Polarization is also used in a ton of different technologies like LCD screens, photography, and even 3D movies.
Wow. So it's more than just like a fancy word they put on sunglasses to sound cool.
Exactly. It's actually a pretty versatile property of light. Okay, now how about intensity and amplitude? I think those might be related.
Yeah, they sound like they could be. What are those all about?
All right, so the intensity of light, that's basically how bright it is, like how much energy it carries. And it turns out that the intensity is actually proportional to the square of the light wave's amplitude.
Okay, wait, back up a second. Amplitude, what's that?
Amplitude is basically the height of the wave.
Yeah.
So a bigger amplitude, brighter light, more intensity. Got it.
Okay, I'm picturing my ocean waves again. So a bigger wave, higher amplitude, more intense light. Makes sense.
Perfect analogy. And this is why high intensity light, like from a laser, can actually cut through metal or do things like surgery. It's all about concentrating that energy into a super focused beam.
Speaking of lasers, this article goes on to talk about some pretty amazing technological applications of light. And lasers are definitely up there, right?
Oh, for sure. Lasers are like straight out of science fiction in a way. They use this process called stimulated emission, and it basically creates this super focused, super coherent beam of light.
Okay, break it down for me. What does coherent even mean when we're talking about light?
It means that all the light waves, they're traveling in the same direction, and they all have the same wavelength and frequency. And that's what gives lasers their like incredible precision and power.
Yeah, I remember all those sci-fi movies I watched as a kid. Lasers were always these super powerful weapons. But obviously, they're not just in science fiction anymore, right?
Not at all. I mean, honestly, they've become such an important tool in so many fields. I mean, think about it. Medicine, communication, manufacturing, entertainment, everything uses lasers. They can scan barcodes at the grocery store and they can perform eye surgery. It's mind-blowing.
It really is. I mean, we've gone from light being this like mysterious thing to something that we can control, like with insane precision.
It's amazing, right? I mean, and we're not even done yet. Think about fiber optics, that uses these super thin strands of glass or plastic to transmit light signals over like really long distances. It's literally revolutionized communication. High-speed internet, global connectivity, it's all thanks to fiber optics.
Yeah.
And that's all about light.
So every time I'm scrolling on my phone, basically I'm interacting with light.
Yep. You got all those cat videos and news articles,
Mhm.
all encoded in light signals, zipping through fiber optic cables all over the world. Pretty cool, huh?
Yeah, it really is when you think about it like that. What other technologies use light in such amazing ways?
Oh, so many. We've got solar energy, for example, which harnesses the power of sunlight to, like, generate electricity. And the way it works, these things called photovoltaic cells, they convert sunlight directly into electricity.
Mhm.
Clean energy, sustainable energy.
Yeah.
And then there's imaging and sensing technologies.
Oh, right, like medical imaging.
Exactly. MRI, CT scans, ultrasound, all these things use different properties of light and sometimes sound to create images of the inside of our bodies. I mean, how cool is that?
It's amazing that we can use light to see, like inside the human body, things we can never see with our own eyes. Or even like the vastness of space, right? We use light to see that too.
You're right. And when we study the light that's coming from all those distant stars and galaxies, we can actually learn so much about them. Their composition, their temperature, how fast they're moving. It's like a cosmic fingerprint.
It really puts things in perspective, doesn't it? All this talk about how light shapes our technologies and helps us explore the universe. But I mean, light's also essential for life itself, right? Like way beyond just technology.
Of course.
Yeah.
Life on Earth wouldn't even exist without light. Think about it. Photosynthesis, right?
Hmm.
The process plants use to make food and oxygen. It all starts with sunlight.
Yeah, it's basically the foundation of most ecosystems on Earth. And of course, we can't forget about, well, us, our ability to see.
You're right. Our eyes are these incredibly complex organs. I mean, think about it. They've evolved over millions of years to detect light, to allow us to perceive the world. I mean, it's really quite a marvel of biology and evolution, all thanks to light.
It makes you wonder what's next, right? Like, will we be able to see things in the future that we can't even imagine right now?
That's a really good question. And honestly, scientists are trying to figure that out right now. But, before we get too far ahead of ourselves, we should talk about another way light impacts our biology, circadian rhythms.
Circadian rhythms, our body clock, right? What does that have to do with light?
Well, you know how important sunlight is, right? It actually helps regulate our sleep-wake cycles. And not just that, our hormone production and even our moods. That's why it's so important to get enough sunlight during the day and to avoid bright light, especially blue light, before bed.
So basically, our bodies are like programmed to respond to light and darkness.
You got it. Exactly. Light is it's not just something we see, it's something we live by. It shapes our technologies, our world, and even, well, us, our biology. Isn't that incredible?
So we've covered a lot of ground here, but it seems like this article is hinting that there's still so much more to learn about light. Like, what's next? What are scientists working on now? What's the future of all this?
Yeah, there's a ton of really cool research happening right now. I mean, light is still a huge area of active exploration, and there's some seriously exciting possibilities on the horizon.
Okay, so give me the highlights. Like, what are some of the areas that you're most excited about? What's really got scientists buzzing?
Well, one area that's generating a ton of buzz right now is quantum computing. I mean, this has the potential to completely revolutionize fields like, well, you name it.
Mhm.
Medicine, material science, artificial intelligence, everything.
Quantum computing. That sounds like Honestly, something straight out of Star Trek. I mean, I kind of get the gist, but how does light fit into all of that? Can you explain it a bit more?
Okay, so quantum computing basically harnesses all those like mind-blowing principles of quantum mechanics. The stuff we were talking about earlier, like wave particle duality and all that. It uses these principles to perform calculations in a totally different way than like your laptop or your phone.
Okay, so not like the computers we use every day.
Right. Not at all. Regular computers use bits, which are either a 0 or a 1,
All right.
on or off.
Right.
But quantum computers use qubits, and those can be in a superposition of states.
A superposition of states? What does that even mean?
It means they can be both 0 and D1 at the same time. Crazy, right?
Yeah.
And this allows them to do calculations that are like impossible for even the most powerful supercomputers we have today.
So are we talking computers that are like thousands of times faster? I mean, how much faster are we talking about?
Potentially, yeah, way faster.
Yeah.
But honestly, it's not just about speed. These quantum computers could lead to breakthroughs in so many areas. I mean, think about like cryptography, drug discovery, materials design. We're
Yeah.
talking about like potentially solving problems that we haven't even thought of yet. The possibilities are, well, pretty much endless at this point.
It sounds like we're talking about like a whole new era of technology, all thanks to our understanding of light. I mean,
Ah.
that's incredible. Okay, so what else? Are there any other like futuristic applications that we might be seeing soon?
Oh, there are so many. But one area I'm particularly interested in is metamaterials. Have you heard of those?
Metamaterials? That sounds vaguely familiar. Refresh my memory. What are those again?
Okay, so basically metamaterials are these artificial materials, like they're engineered to have properties that you wouldn't find in nature. And they can manipulate light in these like crazy ways. I mean, we're talking about almost magical stuff here.
Magical manipulation of light, huh? Okay, you've got to give me an example. I've got to know more.
Okay, so one of the most exciting possibilities, invisibility cloaking.
Hmm.
Yeah, you heard that right. Like, imagine a material that can bend light around an object so that it basically disappears. I mean, it sounds like something straight out of Harry Potter, but scientists are actually working on this right now.
Invisibility cloaking.
Yeah.
Wow, that would be incredible. Okay, are there like any other potential applications for these metamaterials? I mean, besides making things disappear, obviously, which is pretty amazing in itself.
Yeah, definitely. We're talking about advancements in things like, well, imaging and sensing, for sure,
Mhm.
energy harvesting, communication. I mean, we're just starting to scratch the surface of what might be possible. It's a really exciting field.
It really seems like every time we think, okay, we've got light figured out, there's always something new, a new layer of complexity, a whole new set of possibilities waiting to be discovered. It's incredible.
Yeah, it is. I mean, that's what makes science so cool, right? There's always more to learn, more to explore. And light, with all its, well, mysteries, it's still one of the most fascinating areas of scientific research.
Well, I think it's safe to say, after all this, that light is so much more than just, well, what we see. Right? I mean, it's fundamental to our understanding of like everything, the universe. It's driving all these amazing technological innovations. And, well, it's essential for life itself. I mean, how can you not be just like totally in awe of light after all of this?
It's true. It's incredible what we've been able to learn and discover about light. But as we've seen, there's still so much more out there.
Yeah. And that leaves us with, well, a final thought, I guess. Something to ponder as you go about your day. What other amazing things are we going to learn about light in the future? What other mysteries are waiting to be uncovered? The most mind-blowing discoveries might be yet to come. Anyway, thanks for joining us on this deep dive into the world of light. I hope you learned some cool stuff. We'll see you next time for another deep dive.